All right, problem 9, we have how much more effective is exercise and drug treatment than drug treatment alone at reducing the rate of heart attacks among men aged 65 and older? To find out, researchers perform a completely randomized experiment involving 1,000 healthy males in this age group. Half of the subjects are assigned to receive drug treatment only, while the other half are assigned to exercise regularly and to receive drug treatment. So the most appropriate inference method for answering the original research question is, okay, so it looks like we got to figure out what we want to, which inference method we want to look. So let's first determine if it's proportion or means. So you read this carefully, it's talking about how much more effective is blah, blah, blah at reducing the rate of heart attacks, not the number. Just said, and this is very tricky in that sense. It's saying rate, so rate's another way of thinking of proportion or percentages. So it's going to be proportion. I don't know what's going on in my handwriting. I normally write better than that. It's going to be proportion, so it's not going to be D or E. We know that for sure. Now, we're comparing two treatments. We're comparing, exercise and drug treatment versus just drug treatment. So we have two groups. So it's not going to be, one sample. We're going to be looking at two samples. And it's saying, and it's asking for how much more. So like you're trying to get, you're trying to estimate a value, like how much more you're trying to see. Was it 2% more? Is it 5% more? If it was just saying, so it's saying the fact that it's saying how much more, this lets us know that it's a confidence interval. Because a confidence interval gives us an estimate of a range of values for whatever we're trying to figure out. So this confidence interval will give us an estimate for the range of values for the difference in proportion, or telling us how much more effective is the exercise and drug treatment compared to just exercise. Or I'm sorry, compared to just drugs. Compared to just getting drugs. So how much more? If the question was is exercising and taking a medication more effective than just receiving the drug? If it was just like a yes or no question, then it would be a Z test. But since it's asking for how much more, our answer is going to be B. We're going to want a two sample Z interval. All right, and the last multiple choice question, Problems 10.10. Researchers are interested in evaluating the effect of a natural product on reducing blood pressure. This will be done by comparing the mean reduction in blood pressure of a treatment natural product group and a placebo group using a two-sample t-test. The researchers would like to be able to detect whether the natural product receives blood pressure by at least 7 points more on average than the placebo. So 7 points more on average than the placebo. If groups of size 50 are used in the experiment, a two-sample t-test using an alpha level of 0.01 will have a power of 80% to detect a 7-point difference in mean blood pressure. So we have a power of 80% to detect a 7-point difference in mean blood pressure. Mean blood pressure reduction. Oops. If the researchers want to be able to detect a 5-point difference instead, then the power of the test would. Okay, so just think of what happens in real life. And again, they're not saying that there's going to be any difference any different studies or any different sample groups, sample sizes. It's just saying if they wanted to be able to detect a 5-point difference, all other things being equal, what would happen to the power when they want to test a 5-point difference versus a 7-point difference? Now let's first recognize power is a probability. Power is a probability to detect, to detect something being true. So we have this basically says we have an 80% chance of detecting a true 7-point difference in mean blood pressure reduction. But if they want to detect if if the drug, or I guess you could say natural drug, or if they want to detect that this product reduces it by just 5, it's gonna the probability or the power probability or power will go down. The power to detect a smaller difference is, it's harder to detect a smaller difference than is a larger difference. Like for example, it's easy to detect it's easy to tell if, let's say, if you drink, let's say you drink say you're drinking some, coffee, beverage. And you've been getting let's say you've been getting like an average of like 70s on your math test. You drink a coffee beverage and your question is, I want to see if drinking this coffee beverage before a math test will improve my score by 30 points or by 20 points. That's a big number, so you're gonna be able to tell if it's 20 points or more. That's big enough for for it to stand out. But if you were told, let me see, does this coffee, does it detect it by just 3 points? Does drinking this coffee improve my score by 3 points? That's harder to tell because maybe you just get maybe on average your points, your points on a test is gonna be, maybe 5 points different on each test. Maybe it's 75 on the next one, maybe it's 78 on the next one, maybe it's 71. You have fluctuations, obviously, and detecting whether or not those small differences was due to the coffee or not is harder. So it's going to be A. It's going to be less. It's always harder to detect smaller differences than larger differences. I don't know if I rambled on too much, if that made that more confusing, but just think it's the logic. It's easier to detect bigger differences than it is to detect smaller differences. So I hope that helps. Good luck.